I'm going to solve the 2019 3-force method question using the 3-force method. Now this is a graphical solution. Now I don't recommend this for everyone, but it is a solution that you can use. So what we can do is, as long as we know this size, what we can do is we can produce a force polygon that'll look something like that. Something like that. In this case it's probably a little bit higher, but something. Now we know that this force is going out there. We know we have 3 forces. Now in this case it's a little bit easier because I've told you that the angle is going to be somewhere in that direction and this one is pushing up. Now I've talked in the other video how I've determined that, but once I know that I have those, once I find this angle, I can use, as long as I know this angle, which is, I will tell you that it's 68 degrees, and that this one here is 35 degrees, which we're told is 35 degrees. If I know that, I can use that information. If I know that this is 10, I can use that information to find the other 2 sides. Now, the thing I need to do first though is I need to find what this missing angle is. To find this missing angle, what I need to do is I need to find the point of concurrency. Now, the rule is we know this is an equilibrium, and we know that there's only 1, 2, 3 forces. Now we could break these up into horizontal and vertical forces and there'd be more forces, but we see 1, 2, 3 forces here. If there's 3 forces and they're in equilibrium, it means they must be concurrent unless they're parallel. And they're not parallel, so that means this line here meets somewhere. If I extend this line, and if I extend this line, right, let's say for the sake of our argument that they meet, actually my line is not very well drawn. They meet there. So once I've found those 2 lines, I know the point of concurrency for all 3 forces in this diagram. Once I've found that line, right, by joining those 2, I then know that I have a pin here. My force is going to run through that point to that pin. I know that from here, I'm going to have my reaction, the 3rd force, is going to join between that point of concurrency and the point of application of my force. Now, once I've done that, I can then just get a protractor and measure out that angle, 68 degrees. Right? I'm pretty sure it's 68 degrees when we did it last time. Doesn't matter, we're going to run with that as the case. So now I can draw this triangle, and as long as I know that this is 35 degrees here and that this is 68 degrees, I can now, I could just use the sine rule. I'm not going to use the sine rule, but I could use the sine or the cosine rule to solve this triangle, just because I've now got enough information that I could figure out if this is 35 degrees, that makes plus 20 is going to be 125 degrees. 125 degrees there. This is going to be 90 minus, so 22 degrees. I now have enough information that I could just use the sine rule. I could use 10, I said I wouldn't do this, but 10 over sine 22 equals, and let's say I want to find RP, which is what I'm calling this red force. RP is going to equal RP over sine 125 degrees. I can use that method straight away. That will work for me. Now, an alternative is that I can actually reproduce this force diagram by just by drawing parallel lines. Now, how you draw parallel lines, this is where I start to lose students. But something we used to do a lot more when I did the HSC is that we would set up a 1 set square along the line. I call this the heel, and then I slide from there. I will be able to produce a parallel line. Parallel line. Wait. Using my base or my heel and my second as my slide, I can slide and produce parallel lines parallel to whatever I want to draw. Now that's a way, rather than me measuring with a protractor and reproducing it here, I can do that. And once I've done that, I know, well, in this situation here, if I know the value, if I know that this one here, this is an equilibrium. So this triangle is an equilibrium. So if this line here is going clockwise, that means all my values are going clockwise. So if I'm going to call this one here F, I'm going to call this one here, the angle is going to be going down. That line is my angle, and that's going to be called RP. So I can produce a force polygon like that, and I can solve it using the sine rule. Or I can just measure it to scale. So I can draw, if I have my line, so I know I have a vertical line, so I'm going to draw a vertical line, and I have a line at 35 degrees, and again I can use, it's a bit hard at this scale, but if I set this up to the correct angle and I slide down, I can eventually produce parallel lines. So produce this one, in this case I'm just going to draw it roughly 35 degrees. And then I have this angle, which is going to be a little bit more than 60. I can do that just by drawing this parallel. Once I have that parallel, if I then set this to the scale, so I'm going to set this to the scale of 10 millimeters equals 1 Newton. And now I'll draw this vertically. I now have a scale version. And now I can measure, this is 10 millimeters to a Newton, so 10 Newtons is 100 millimeters. The value of F is going to be, I get 13 Newtons. The correct answer is 14 Newtons. And this one here, I get 21 Newtons. The correct answer is 22 Newtons. Now, I'm okay with having that number being off. I'm okay with having that off being up to 10%. So, especially when I'm using, I mean, they were all drawn pretty rough. So, just to get the actual value, the reaction at P equals 10 sine 125 divided by sine 22 degrees. The correct answer is, for RP, is 21.87 newtons. Pretty close to 22. Now, to me, that's close enough. Now, and for the HSC, that's close enough. So within 10% is my marking error, at least until I learn otherwise. So this is how we do the three-fourths method. I'm not saying it's for everyone, but it is an alternative to using the moment method to solve these questions.